Okay, my screen is visible. If someone please reply in chat box, so that will be help. Hello, am I audible? Hello. Yeah. Okay. Thank you. Yeah. So okay. Sorry. So good evening, everyone. Welcome all to this in online NPTEL course, Analytical Chemistry. The course instructor is Professor Devasis Ray from IIT KGP, and I am Subhankar Mandal from IISc Bangalore. So we are now in week 5. So basically, spectrochemical method for analytical chemistry. So last week I did not give so much time because I was busy with some experiment. So last week basically we have discussed only the question about for week whatever spectrochemical method we have learned. So basically this is the continuation of that one only. So basically in lectures 20 we have learned about the absorption spectroscopy and instrument method as well as Beer-Lambert's law, and then different transition like metal metal transition or DD transition, then metal to ligand transition or pi to pi star transition or organic compound, and pi to sigma star transition. And then lecture 23 also we have learned about the what is called AFF transition and different type of chromophores and their application, and how we can use chromophore to use the non-color compound. So that basically chromophore basically some part of the molecule which is which is applicable for the color of that compound. So and then if you have two compound and if you want to measure absorption spectra for two compound in one mixture, so that we have learned in lecture 25. Okay, so basically this is the lecture 21, lecture 20. So basically here which color we should observe when some compound it absorbs some light. So we also discussed these things in first class. I think there I think we have learned some color circle. So basically this thing only, suppose we have this circle, so you can start from here with geo. V, G, Y, O, R. Okay, so if some this is the color circle, so whatever it is written here, so I just written in the circle so that it is easy to remember, or no need to remember, just you can write the things, and according to this if any question will come, then that you can solve the question. Okay, so Vibgeo, if something is absorbed, so suppose some light is absorbed, some compound is there and that compound absorbs some light here, so then you will observe in eyes in this what is called complementary current, that is its opposite, so Y, so that is yellow color. So basically yellow color we will observe. If violet region, like suppose it is the compound absorb the light near this region, 400 to 435 nanometer, then you will observe the yellow color, and that is near 550 to 595 nanometer. So if you absorbance spectra, then you will see the absorbance spectra near 400 to 435 nanometer. Okay, so and so along with this, here you can we have learned that if some compounds which has same color, like pink color for uh, pink color for what is called zinc, and pink color for lead. So for this compound we have to choose some other reagent which can separate these two metal center. Okay, so these things we have learned in lecture 20, and we also discuss in first class also. So I am not discussing more details on this, so we'll go to next slide. So basically from here it is started. So how the absorbance spectra or absorbance what is called UV visible principle, or how it is work. So basically here we have some light source, and that is tungsten for visible light, and deuterated source, that is for UV region. So when there is some filter or the monochromator is there, where you can, because in deuterium and there is so many light source, different wavelength light is there. So but we need some monochromator light which is a particular one wavelength light, so that it can absorb particular sample for a particular wavelength. So we can get the absorbance spectra at a particular region of wavelength. Okay, so and here you have the sample, basically some cuvette you have. Okay, and you have some case sample, color sample, and this I0 is coming, and this length is L. So and after absorbance it is transmitted I, and it is detector is there, so it is detect here, and after that whatever spectra we are getting, absorbance versus as a function of wavelength. So you will get the spectra like this. Here is the wavelength, and this is the absorbance, and you will get some spectra. Suppose it is like this. Okay, so this is the okay, suppose this is 500 nanometer, some absorbance is happening. So for that you will get the absorbance spectra like this. Okay, so and here I can show on video where okay, so there how the observance instrument is. So this is the thing. So in UG course I was the T, and Dr. Achinta Jana was the lab instructor. So basically you can see here, this is the okay, so this is the visuals instrument. So this is the instrument. So basically this side you have the source, and along with this some detector also there, monochromator is there, so that only one particular wavelength light you can observe. And here is the sample holder. So basically here you can see the cuvette. So basically there, this is the UV cuvette. So in UV cuvette, one part is transparent and other part is what is called not light transparent. So basically light will come and go, and this side you have the detector. Okay, so if you see there, so this is the basically first you have to take the solvent spectra. Basically if some whatever contribution is there in solvent due to the solvent, so that we have to minimize. For this, before starting the experiment, first you have to take the reference spectra. Okay, so this is, and you can see the transparent part you have to keep along the light path length. Okay, and you just, this is the software, I think EV lamp, this is the software. So first you have to take the blank one. So it's depend on the different software to software. So first you have to take the blank one, so that whatever blank or whatever solution is there, due to that if anything is whatever contribution from the solution, so that we can minimize. Okay, so after that I think this is some photo degradation experiment. So basically in TiO2 presence of TiO2, some deconvolution, what is called dissociation experiment with time. Okay, so I think I can, yeah, so this here the blue color solvent is there, where you can put in the cuvette, and you have to wipe with the cuvette, so that whatever transparent region is there, so that should not be any finger mark or something. If you have some finger mark, then it will affect on your measurement. Then after that you have to do in sample thing. Okay, so now you'll get some spectra, basically the absorbance spectra. Yeah, here you can see there is two absorbance spectra. One is near 650 or 640 to 680. This is one spectra, absorbance peak, and another one near below 300. So this is another absorbance peak, and one small harm is there. So basically this is the UV visible instrument. So that's all. Then we can come to the slide. Okay, so that's how we can measure the experiment, and we also know that this absorbance spectra also I have discussed earlier also. Just once we remember, so absorbance basically logarithm part minus log of transmittance. So basically from there we can get minus and log of transmittance means whatever I by I naught. So basically if you inverse it, then it will be log I naught by I. Okay, and from the Beer's law we saw the relation that A proportional to concentration. Whatever concentration you have, its absorbance is proportional to concentration, and from Lambert's law its absorbance proportional to length or length of the cube. So basically what is the thing is, if your length is high, then your absorbance will be high. So then you will apply some proportionality constant epsilon CL. So this is the absorbance coefficient. So from there we get this expression. So these things all we know, so I am not spending so much time on this. Okay, so last week also I discussed some protein sample, what is called stability thing. So from UV visible spectra we discussed that we can measure the stability of the hemoglobin. So this is some experiment on of my student Aratrika Sarkar from she is 12th standard student. So she did some his project on protein stability of hemoglobin with pH and temperature. So basically she made two sample, one pH 9.2 and other one is pH 7. So and you can see there is two cuvette, one for reference spectra and other one for your sample. Okay, so you can see that in the reference spectra the blank solution is there. So that's why whatever when you will measure the compound of your sample, that time you first you have to take your blank sample, and here after that you have to take your what is called protein sample. And this is not exactly a UV cuvette, because there you can see both side are transparent. Actually in UV cuvette this and this part will be transparent, this one is not transparent. This is the fluorescence cuvette, where usually your detector in fluorescence measurement, it is in the what is called 90-degree angle. So for this part light will come and this side your detector, and but in UV visible spectra there is your light source and this side your detector. Okay, so here you can see we also discussed that with pH your protein stability will change. Here you can see this black one is the pH 7 and blue red one is pH 9.2. So basically hemoglobin there is heme moiety is there, along with this the globular protein is there, and that globular protein are connected with the what is called hydrophobic interaction and van der Waals interaction. So different OH or hydrogen bond is there. So with pH your hydrogen bond the hydrogen bond number of hydrogen bond will change. But along with this your protein structure or secondary structure of your protein also will change. Okay, so that's why you can see with pH also the intensity of your absorbance spectra is decreasing, which indicating that the your what is called your absorbance spectra, your protein structure also changing. So this, if the absorbance spectra is decreasing, that means your stability of the protein structure whatever it is there in the initial state, that is decreasing. So here you can see in this is for pH 7. Okay, so in pH 7 you can see with temperature. So this is black one is room temperature, and along with this when the temperature is decreasing increasing, your absorbance spectra also intensity also increasing. So this one is absorbance is here, actually this is non-background subtracted. So if you do background subtraction, then it will come maybe here something like this. So that time you can see the absorbance is decreasing, so which indicating that your protein stability is it's decreasing. And this is a pH 9.2. so here you can see here also with temperature the protein stability is decreasing. Okay, so and for this we also discussed that it's 7.4 is the particular pH where all the enzymatic reaction or whatever protein and enzyme used to work properly. So for this all the enzyme or whatever in our human body, whatever pH, it is around 7.4. Okay, so this is basically from last week thing. And this one in this here we have discussed or we have learned different transition, basically metal to ligand transition, and how the with metal center the absorbance spectra will change. So basically this is one of the paper where we have measure the UV visual spectra of different transition metal phthalocyanine. So basically this is the metal center and this is the phthalocyanine ring. Okay, so the here actually we have used this compound in different application, but I have shown this one that how we our absorption spectra can change with oxygen, or what is the spectra for different transition. Okay, so here you can see that manganese, iron, cobalt, nickel, different transition metal we have measured. So here you can see this key band is known as the Q band, which is due to the transition for A1 U to Ag star orbital. So basically this key name is came from the crystallography symmetry structure. So I think whoever from master student or UG student of third year, they know all these things. So I am not discussing how this nomenclature came. So I just mentioning what is the transition for this. Okay, so and this spectra this is known as B band, and this is due to the transition from A2U or B1U to Ag star orbital. Okay, so and this band, and here we also discuss the metal to ligand charge transfer. So this is near 500, this is the metal to ligand charge transfer. Okay, And here, as here our motivation is how the absorbance spectra will change if we introduce oxygen molecule, because oxygen can, as it is a square planar complex, it can coordinate this fifth position, and it can coordinate with sixth position. Okay, so if sixth or fifth position it is coordinate with the oxygen, then it can change your energy level of the of what is called transition, because we also discuss, or we have learned that suppose transition from E1 to E2 transition, this is your HOMO and this is your LUMO. So if transition, then due to this transition there is some absorbance spectra will observe. So if your HOMO LUMO energy will change with different analyte or different reagent, then your absorbance position also can change. Okay, so here this is the motivation, and other motivation is how the absorbance peak will change with the different metal center. Okay, so here you can see this blue one is the argon atmosphere, that is basically inert atmosphere, we have measured the absorbance spectra, and in oxygen atmosphere this is red one. So here you can see the Q band, which is characteristic peak for the this phthalocyanine ring. So this is disappear. And also in iron sample also you can see that in presence of oxygen, the red one, which is due to the oxygen atmosphere, so it is shifted towards the higher wavelength. So basically when the oxygen is coordinating, that means the energy gap between the HOMO or LUMO is decreasing. So for this it is shifted towards the higher wavelength. Okay, but in the case of cobalt and nickel, you can see there is no such effect on this, because how your oxygen is coordinating with the metal center, that depends on the change of the HOMO and LUMO. Okay, so for this you can see that for cobalt and nickel it is not shifting, because as we are going from manganese to iron to cobalt or nickel, so as we see the d electron is increasing, number of d electron is increasing. Okay, so as the d electron increasing, as oxygen also lone pair is there, so the lone pair interaction is there, is repulsion is there. For this the coordination or interaction is not so strong, so that we are not able to what is called observe what is the effect of oxygen for cobalt and nickel. Okay, but here you can see the data for different metal, transition metal, for nickel, copper, zinc, all these things. Here you can see that from iron to nickel, the peak position is of the Q band is shifted to the higher wavelength. Okay, what is this? Because there is two factor is working. One is electron repulsion. Okay, another one is electronegativity. Of metal center. As you know, from in a row we are going from left to right, then the electronegativity is increasing. Okay, if the electronegativity increase, then your HOMO is more stabilized, then your LUMO and HOMO band gap is will increase. But if dd electron is repulsion is there, then your HOMO energy will increase, so that your HOMO LUMO gap will decrease. Okay, so here you can see that as electronegativity increase, but these two things are working in different direction. As you can see, as the d electron is in number of electron is increasing, the wavelength is going to the higher wavelength region, means your HOMO LUMO band gap is it is called decreasing. That means the electron repulsion is more prominent compared to your electronegativity of the metal center. Okay, So this is the things, this type of information also we can get from the UV visible spectroscopy or absorbance spectroscopy. Okay, so I think next we can discuss some question. Okay, so you can write in the chat box. So what does a spectrometer measure? Okay, what does the spectrometer observe? Amount of both heat and light absorbed by a sample. Okay, Anjali Prasad C and Bhanu Prasad also C. Okay, so whatever we have absorbance spectra, basically what we have learned in the, we also it is called discuss earlier also. Basically your absorbance, your sample is here, your light is coming, I naught, and this is your I, and there is detector and there is source. Okay, so here basically sorry, this is I and this is I naught. So basically you are measuring the absorbed light, whatever absorbed light is absorbed by the sample. After that, whatever light is transmitted, that is going to the detector. So among here we are not measuring any heat, because there is no that kind of thing. So only the light, whatever light is absorbing and whatever light is coming, that one we are measuring. So amount of heat absorbed by a sample, that things we are not measuring. So amount of light absorbed by the sample, that things we are measuring. So this B is the answer. So I think we have discussed this thing, that with temperature that may be confused. So basically here with temperature we are means in certain temperature we are keeping the compound, then we are measuring the UV visual spectra. So whatever heat, that things we are not measuring here. Okay, so the next question, which light source can be used in absorbed UV visible spectroscopy? Tungsten lamp, fluorescent lamp tubes, incandescent bulb, or glower? Okay, Bhanupasa region, fluorescent tubes. Okay, Sally written C. Okay, Anjali Prasad, tungsten lamp. Okay, so we also discuss here also that we can use tungsten here, W tungsten, and deuterated iron. Okay, so basically what we are measuring here, that we are measuring absorbance as a function of lambda. Okay, and UV visible region you are measuring. So that means whatever what is called light source you will use, that region, your means light region should be in this UV visible range only. Okay, so if there is what are the option? So tungsten, if you see tungsten, the wavelength is around 350 to 2200 nanometer. Okay, so this range is the tungsten. So and after that we are using monochromator. So in this region our UV visible also 300 to 800 nanometer. So that is also 200 to 400 800 nanometer. So that is the UV visible range. So this range is covered by this tungsten lamp. So if you see other lamp like what is called glow bar, so this is 1200 to 40,000 nanometers. So this is not covering this region. Okay, and this flow this is the hydrogen or helium, also it is not in the mention. So basically hydrogen or deuterium, that is the energy range is 160 to 380 nanometer. So this will cover the UV range. Okay, so in the what is called UV visible spectrometer, whatever we have seen there, one is tungsten is there, another one is deteriorated deuterium is light source is there. So these two things is there which can cover the range from 200 to 800 nanometer. Okay, so the answer is A. So which one among the following, if present in color complex of metal ion, decrease the absorbance? I think if you could have observed the means watch the lecture, then you can easily answer this. Okay. So here something is there which can decrease the absorbance. It means suppose you have some absorbance spectral lambda. So and there is a color compound, and for that your absorbance value is like this. And suppose you have something which can forming with the, suppose you have metal complex MLN, and in this one is a color compound, and you are adding something which forming suppose ML n minus 1 BA, so which is this AM and A complex, that is colorless, so that your color concentration or absorbance is decreasing, suppose here. Okay, so this is the thing. So here I think we also learned there that if the sulfate or phosphate group is there, then that will sulfate or phosphate PO4 3 minus. So this group is present in your compound or solution, then it can easily form, or it is tendency to form the metal complex with metal sulfate or metal phosphate with used to form, which is a colorless compound, so that your absorbance value will decrease. Okay, so the answer is phosphate group. Okay, next question is, what is the characteristic wavelength of acetyl salicylic acid in UV visible spectrum? Okay, Bhanuprasad have written B. B means 370 nanometer. Okay, Anjali has written A, 285 nanometer. Yeah, so correct answer, if you see the structure, this is the salicylic acid. So in the benzene ring 1 and 2 position, as one acetic group and one ester group is there. So basically this is it has the characteristic of 285 nanometer, and this is the what is called anti-inflammatory drug. So uh, and it is its epsilon value is around 400. 400 what is called, what is the unit of epsilon? Absorbance epsilon Cl. C is the concentration, L mole per semi, and this is length in semi. Mole semi. So mole per semi, if it is, then absorbance is, that is liter mole inverse semi inverse. So basically it will be liter, this is the absorbance, it will divided mole semi 2, then liter mole square semi cube. Okay, so this is the epsilon unit. Okay, so next question you can go. So in unconjugated alkenes, pi to pi star transition takes place around which region? So there is 4 options, so if people can try. Krishna B, 170 to 190 nanometer. Okay. So this is unconjugated alkenes. Okay, so Krishna has told right answer. So this is the answer, 170 to 190 nanometers. So basically, if you have this is pi star transition. So if you have carbonyl, then what is around the pi to pi star transition, where it is to happen, pi to pi star around 190 nanometer, and epsilon value around 900. Okay, and if you have n to pi star transition, then 280 nanometer and epsilon value around 15. Okay, so and this is the thing. So this is the answer, 170 to 190 nanometer. But the pi n to pi star transition, this is what is called symmetry forbidden transition. So this is symmetry Forbidden transition. So as it is symmetry forbidden transition, that means okay, whatever absorbance peak will come, that intensity will be low. Okay. So you can go next question. What is the maximum absorption wavelength of caffeine in UV visual spectra? UV spectroscopy. Okay. Basically, caffeine is very important compound. So this is basically uh, what is called alcohol. Naturally, alcohol. It's usually you can get from in leaves of tree. So different type of trees leaves you can get this caffeine. So basically, the characteristic absorbance peak of caffeine is 72 nanometer, and it's this is the structure of this compound, and its epsilon value around 1000. Okay. So what is the maximum absorption wavelength of caffeine in water? So here you can see that it's what is called 272 nanometer. It's in the solid state, but if you are dissolved in solution, then there might be some as you are it is called dissolving in water, so which is a polar solvent. So as here you can see the carbonyl group also there, so the lone pair is there, so there is a chance of protonation. As a result, your absorbance peak might be changed. So what will be the answer now, you can tell? So I think this is very easy, because whatever 272 nanometer you're in solid state. So actually, yeah. So whatever things we have discussed, that is in solution state. So solid state also you can do your compound absorbance spectra. That case, usually KBR plate you have to make. Basically, KBR is the UV transparent. Okay. So it is UV transparent, so you can mix your compound with KBR and mix properly, and then you can make a palette of these things, and you can measure the UV visual spectra in transmittance or reflection mode. Okay. So the answer, I think this one has in solid state, this is 272 nanometers. So if you draw add it in what is called solution or polar solvent water, then it will shift a little bit to the higher wavelength region. So for this it is near 280 nanometer is the absorbance position. So here you can see the as a function absorbance as a function of wavelength. So the highest peak it is coming near to 80 nanometer. Okay. So what type of charge transfer transition occurs if the complexes have ligands with relatively high energy lone pair, com- example sulfur or selenium, if the metal has low lying empty orbital? Okay, here you can concentrate on this one, ligand with relatively high energy lone pair and metal has low lying empty orbital. So these two things if you concentrate, then I think you people can easily answer. Okay, so whatever we have discussed earlier also, suppose you have E1 on ground state energy and this is E2. Here your electron is there, that means this is your HOMO and this is your LUMO. Okay, so suppose you have some energy you are possessing, so whatever your absorbance electron will go to the upper energy level, so that your absorbance spectra will observe. Okay, now here you can see that your ligand has higher energy. Suppose you have a ligand and like this, and this is suppose ligand HOMO and this is ligand LUMO. So basically as your ligand has higher energy, so electron can come from the higher energy to lower energy of what is called LUMO state of your metal. Okay, as the electron is transferring, as a result you can see some spectra in the absorbance spectra. Okay, so as a result this absorbance spectra corresponding to metal ligand to metal charge transfer, as the electron or charge is transferring from the ligand HOMO to the LUMO of the metal, so it is ligand to metal charge transfer. Okay. So as in the question it is mentioned the ligand with relatively high energy lone pair. So lone pair means you have, this is suppose n orbital and you have the lone pair. Okay, and that is the HOMO. And metal has low lying empty orbital, that is the LUMO of metal center, which is a lower energy. As we know that from higher energy to lower energy the electron usually transfer, so that things due to the ligand to metal charge transfer. So next question, which among the following reagent can be used as a reagent for simultaneous spectrophotometric determination of lead and gold? So lead in +2 oxidation state and gold is +3 oxidation state. Okay, I think the answer is B. So this is Meperazine hydrochloride is also known as MMH. Okay, so basically if you have lead plus 2 complex and AU plus 3 complex. Okay, so if you add these compounds, then this compound will form the chelate complex. So that is orange red in color. If lead complex, it is form orange red color. Okay, and for gold, it is from blue in color. Okay, and the absorbance value for this, it is 3.6 into 10 to the power 3 liter per mole inverse centimeter inverse. Okay, and for this blue complex, its absorption value is 1.3 into 10 to the power 4 liter mole inverse centimeter inverse. Okay, so this is the thing. I think this is the last question. So which is the example of metal to ligand charge transfer among the following? So one is lead oxide, one is cadmium sulfate, one is KMnO4, other one is some iron organic complex. Okay, so metal to ligand charge transfer. So basically you have to think that suppose you have some compound and which has a molecular orbital and the what is called homo, that is metal like character, so that you can metal to ligand charge transfer, basically metal like character. Okay, and what is the LUMO, that will be ligand like character. Okay, so if you what is called crystal field theory, if you CFT, so if you attend that course or somewhere, then you can easily means understand this, what is metal like character, what is ligand like character, or molecular orbital theory. So that things also you can get to know. So here basically it is the answer is D, basically the often, that is a organic compound. So in organic compound pi star orbital is there, so in the pi star orbital it is a low lying orbital. So as a result you can see that it is a means metal which is a high energy state, so it is plus 2 oxidation state. So as it is a low oxidation state, it can transfer electron to metal ligand pi star orbital. So you can see the metal to ligand charge transfer, because all other things is a what is called inorganic compound, and it is only this case only the metal to ligand charge transfer can be possible. Okay, so I think all the question is over. So I think also time also is over. So basically as we are discussing about the it is called absorbance spectra, so this is where last time I went. So this is the X-ray absorption spectra DG. So does electron synchrotron. So basically here is the what is called a synchrotron, means high energy electron source. Okay, so this is if you want to see some particular molecular structure or oxidation state or coordination sphere, because we are discussing about different type of metal complex or complex compounds. So if have you have some metal and along with this some what is called ligand moiety is there, then how the ligand moiety it is, what is the structure, that is octahedral structure or tetrahedral structure, all these things you can get to know from high energy synchrotron X-ray absorption spectroscopy. So this is in Germany. So and this is the setup of X-ray absorptions. I think this is the XF's measurement. Okay, so this is the source and this is the transmission detector. If you want to measure in fluorescence, this is the fluorescence detector, and here is the sample. So your X-ray is coming from here, and here you are detecting. Okay, and if you are measuring the detection, it is called fluorescence mode, then you have to do in 45-degree angle. Okay, so this is transmittance as well as fluorescence mode you can measure, and this is the operando spectroelectrochemistry. I think in this course also we will learn about the spectroelectrochemistry. So that time I will discuss a little bit more about this. So basically you are doing some electrochemistry. This is the potentiostat and this is your cell. So you are measuring in fluorescence mode. So here some electrochemistry occurring, and along with this you are measuring X-ray absorption spectra. So also you can measure UV visual spectra also. So basically some other experiment is going, or other electrochemistry or something, some pressure or some temperature, something you are changing, and along with this you are measuring some spectroscopy. So that is the spectroelectrochemistry or spectro operando spectroscopy. Okay, so this thing quite interesting, so we can what is called discuss more about this later. Okay, so I think today up to this only. If you people have some question, you can ask. Okay, I think one has any question maybe. Okay, I'll wait for 1 minute. Yes. Yes, Surya. Sorry, I did not get your question. Okay, you want to measure or heat you want to measure, means how the heat is changing. So basically in that case there is not spectrometer is not actually. Basically what how whatever way we are measure the temperature, like some thermometer or something you use. So uh, if you want to measure the stability or something, means how much your compound is stable, that kind of things if you want to measure, then you can measure DSC. So differential what is called thermal spectroscopy. So that things you can measure, but you can what is called only something is happening in your system. Suppose temperature is changing and you are changing from externally, then that thing you can measure by some whatever way we measure some temperature parameter. So but if you want to measure some thermal stability of your compound, then you can measure DSC or thermal gravimetric analysis, whatever thing. So that things I think we will discuss later maybe. Hmm. Okay, I think we can call up the meeting. Thank you everyone for joining.